Hello, my name is Ryan Michela, and this is a talk about how we use Helm at Salesforce to tame our Istio configuration. So Helm doesn't always get a lot of love, but I hope by the end of this talk, you'll see Helm as a critical component of your Istio deployment. In this talk, we're going to look at Helm from a new perspective. We're going to see how Helm is a perfect fit for automating many of your day 2 operational tasks. Finally, we're going to look at how Helm and Istio can work together to create a seamless GitOps experience for your developers. Let's talk about Helm. Helm calls itself the package manager for Kubernetes, but I think this sells Helm really short. For me, I see Helm as a Swiss Army knife for Kubernetes. Sure, it can install packages, but with a little creativity, it can do so much more. So what does Helm do, according to Helm? The base unit of functionality in Helm is a Helm chart. Given a chart, we can perform basic management operations like installing, upgrading, and rolling back. That's what Helm says it does. Now, a Helm chart is just a collection of YAML files bundled together in a tarball. The chart contains a Kubernetes object definitions for each component to be installed and a values.yaml file providing additional parameters for the installation. When you run the Helm install command, Helm combines the chart, the values file, and additional parameters from the command line and pushes the output to the Kubernetes control plane where it's made real. It seems pretty simple. But you will quickly find that Helm has a polarizing reputation within the Kubernetes community. First, many of the public Helm charts are either broken or incomplete, and you'll often have to fork those public charts to make them fit into your environment or comply with your security requirements. This kind of defeats the purpose of using public shared Helm charts. Second, custom resource definition installation is not a solved problem in Helm, or in Kubernetes for that matter. This results in sometimes intermittent installation failures caused by race conditions in Kubernetes and is exacerbated by the proliferation of Kubernetes operators, each coming with their own CRD. Finally, writing charts from scratch for everything in your cluster seems tedious and redundant. Like, why would you write a chart if you already know all the Kubernetes YAML you want to write, or you want to install? Why wrap it in the complexity of an added chart? Finally, additionally, prior to Helm 3, Helm's tiller component presented a major security or vulnerability if you didn't adequately secure it. Well, the good news is you don't need most of Helm to get the most from Helm, and I'll show you how. Helm and Istio really do go hand in hand. In fact, you used Helm to install Istio whether you knew it or not. The Istio operator and the Istio control command both embed Helm charts for their installation. Also, Istio ships with a Helm 3 chart for manual installation. Under the covers, Helm is just a wrapper around Go template. It's pre-wired to support the Sprig function library and a collection of native functions. The Helm template command joins together the values file with chart metadata from the template to form a template context, which is then passed to the Go template engine, which executes each template in the chart against the context and concatenates the output into one big piece of text. You see, Helm just isn't a package manager for Kubernetes. It's a general purpose Go template engine with some Kubernetes specific idioms sprinkled in. So if Istio runs on YAML and Helm can emit arbitrary YAML, we can manage all of the aspects of our Istio configuration with Helm, not just the initial installation. Now, why would we want to add the additional complexity of Helm to Istio's already complex configuration? Well, it's because Istio's configuration is both too flexible and too granular for everyday human consumption. Most users don't need most features of Istio. You still have to interact with them to write valid Istio config. Put a different way, the scope of users' intent is mismatched with the scope of system configuration. However, using Helm charts to generate our Istio config lets us plaster over Istio's inherent complexity with simplified facades. The values.yaml file from your chart becomes a domain-specific language where we can configure our services in the same way we think about them. Now we can use a Helm chart template to render the high-level representation of our service into the low-level details Istio expects. This aligns the scope of our intent with the scope of our configuration. This idea is really best expressed with a demo. So why don't I show you how this works? What we're going to do is we're going to install the Istio book info demo. And I've just got my little localhost here, product page, lvh.me, just a local loopback domain. And as you can see, nothing's loading. So book info product, this is the top level service of the book info demo. And I've created this values file for our chart. This is how we express all of the details about this book info service in a single file from the perspective of an application developer or a service developer. So at the top, we have some coordinate information about the service, what system it's part of, what service its version. We can specify a service account. This will be the book info product service account, and we're going to create it. This is important because service accounts drive Istio identity, which is then used to drive Istio authorization. We have replica and auto-scaling configuration coming down next, where we can say how many we want initially, how many would be unavailable, horizontal pod auto-scaler settings, our Docker image coordinates, a list of our ports, both the external port from the outside and also the internal port from our pod, configuration of our ingress gateway. We're going to bind to this service to the default Istio ingress gateway on the lvh.me host, which is just a local loopback, matching to these specific set of URL prefixes. Finally, we specify our pod resource settings and our probes, just to keep things up and running. So if we install this with the simple Helm template, namespace default, then that is the book info product. Oh, there we go. Helm template, namespace default, book info product, and kube control apply. We're just going to run that thing through. Give it a moment, and we can see one file that we used to specify our service from the developer's perspective created a pod disruption budget, a service account, a service, a deployment, a horizontal pods autoscaler, a destination rule, and a virtual service, all created from this chart. If we go ahead and reload, we can now see book info's top level service is running. But you'll notice we're not picking up the details or reviews from those respective services. So let's look at the book info details service. It has a value YAML. It is nearly identical. The only difference between this and the book info product is that we're not specifying ingress gateway configuration. So if I install that, book info reviews, we're doing details. So let's just go ahead and do that. We installed the details service. It created all of our objects. We give that a moment to synchronize in Kubernetes and Istio. And there we go. Our book info details service is running. Repeat the same process with book info reviews, which is once again identical. And once that starts up behind the scenes, it's a little bit longer to boot this service. While we're waiting for that to start up, why don't we take a look one level down and look at what gets created when we boot our product here. Behind the scenes, we've got a bunch of different templates. Each template is a different part of the Kubernetes or an Istio configuration. So for example, we've got our deployment. When we create our deployment, it looks like templatized Kubernetes YAML. The nice thing about this particular about these charts is that we're also specifying all of the preferred Kubernetes labels. Down here, we've got the Istio labels that are required for making Kiali happy. We've even got, we're even creating a config map if needed, and automatically reloading the service if the config map changes. So we're creating deployments, we're creating virtual services bound to gateways and hosts. And you can see this is all just Helm configuration. There we go, our review service is up. Developers don't have to interact with the low-level details of the chart. You make the chart once, and then developers operate at the much higher level of the values file. This is what I mean when I talked about the domain-specific language for describing your service. Now let's do another example. We've got our services configured very quickly using three different charts, but now we want to set an authorization policy. So I have a different chart with a different domain-specific language for describing mutual TLS policies in Istio. If you go out of the box, Istio's mutual TLS policies are pretty low level and require a lot of low-level details to get right. So what we do is let's make them a little more high level and easier to reason about. At the top, we've got namespace policy. This identifies for a namespace we want to set up default deny or not. Default deny would be to make it so all requests are blocked unless they're explicitly authorized. And additionally, we're going to switch our mutual TLS mode to strict. Below that, we're setting up a list of authorizations, one for each service. So the book info product is authorized to receive requests from the principal Istio Ingress Gateway Service account to these specific paths. Below that, the book info details and the book info review services are allowed to receive requests from the book info product service account to the details and reviews paths respectively. This is a much simpler way of thinking about mutual TLS, and to show that it actually is working, I'm going to go ahead and we'll comment out all of the authorizations. We will apply book info auth There we go. Applying auth policy, and since we commented out these service-specific authorizations, we got a default authorization policy and a default peer policy created in our namespace. And if we reset, once we give this a moment for Istio to resynchronize, there we go. RBAC access denied. So let's open back up the first service, the book info product service, receiving connections from the Istio Ingress Gateway. And that has created this book info product authorization policy in Istio. Now the top level product service is back up and running. Well, there's some cached. Got to get through the cache. There we go. Now it's back up and running. If we repeat the process, we can now turn on the authorization policies for the supporting services. We get more authorization policies created by the chart. And once we get this back up and Istio synchronizes, you can see that communication is once again flowing. Mutual TLS described in a single document, a single file, and this can be version controlled. You have version history, you can see who made changes to your authorization policy, all from a single chart. Let's look at the last chart for another common use case that's really easy to manage with Helm charts, and that's Istio egress policy. So this chart is really useful when you've got egress set up to block anything that's not in the Istio registry. It's the registry only mode for egress. And so what we want to do here is recast how we think about Istio egress in terms of mediated and unmediated TLS. So mediated TLS is when your application makes an HTTP call to something in the outside world, like Amazon or Wikipedia. And the Istio proxy converts that HTTP call into an HTTPS call, originating the TLS from the proxy. When you do this, you get a lot of benefits because you can then configure connection policy like retries, and circuit breakers, and timeouts, and all sorts of low-level protocol-specific things that you don't have to put in your application code. The alternative is unmediated or pass-through TLS, which is when your application code makes an HTTPS and encrypts the connection in code, in which case Istio really doesn't have a choice but to pass that through as a TCP connection. It has very little visibility to the internals. Even still, you still want to be able to set up a service entry for that for that route so that Istio will know about it and allow it through your proxies. So with this chart, we're able to identify the mediated TLS versus pass-through TLS. And for the mediated TLS, we can put all the different connection details and set them up. And if we install this, which is the egress chart, it's actually creating a bunch of components under the hood, which you'd have to maintain manually. It really takes you away from this high-level concept of mediated versus pass-through TLS and gets you thinking about the low-level details of destination rules, service entries, and virtual services, all of which have to be perfectly crafted for egress to work correctly. So what did we see? First, we simplified the Istio book info sample so that only the important aspects of each service were represented in a single file. Next, we enabled mutual TLS security using a single source of truth written in a clear DSL. And then finally, we used a different DSL to describe our meshed egress policy in terms of mediated and unmediated TLS, rather than in terms of low-level Istio primitives. It's also helpful to reflect on what we didn't see. We didn't directly interact with any low-level Kubernetes or Istio configuration objects. In fact, we expressed our intent and let Helm turn that into config. As we've seen, Helm charts are a powerful tool for managing service configuration in Istio. But as the number of services increases, so does the number of charts. So how do we handle this increasing complexity? Well, that's where Helm Starters come in. According to Helm's documentation, you create a new chart using the Helm the Helm create command. But in my experience, the default Helm chart is simultaneously overcomplicated and underexpressive. It does little to shield you from the underlying complexity of Kubernetes, and it knows nothing about Istio. Now, you could copy your charts from one service to another as needed, but copy-paste is suboptimal and brings along a lot of baggage. Luckily, Helm comes with a barely documented feature called the Helm Starter. A Helm Starter is a Helm chart that makes Helm charts. Once installed, you use a starter by passing the -- starter parameter to the Helm template command. At Salesforce, we built the 4 common starters you saw in the earlier demo. The Mesh Service Starter packages everything you need to run a service in the mesh. The Ingress Service Starter is like Mesh Service, but adds ingress gateway configuration. Mesh Egress configures egress routes from the mesh. And finally, Auth Policy configures Istio authorization rules for mutual TLS. Links to this presentation and the GitHub repo will be posted in the IstioCon Slack after this talk. So far, we've talked about Helm, what it is, and how it works. We've looked at how Helm charts can help us think about Istio configuration at a higher level by creating a domain-specific language for our mesh configuration. And finally, we saw how Helm starters can help bootstrap new Helm charts. So I'd like to conclude by showing you how my team uses all of these concepts put together to create a unified GitOps strategy built on Helm. Our GitOps strategy for Kubernetes and Istio starts when the developer creates a new service. As part of starting a service, the developer uses the Helm Starter to initialize the service's Helm chart. After final adjustments, the chart is checked in and our CI system builds the chart with the Helm package command. The Helm package step packages the chart into a tarball, which is then staged into S3. Next, a Spinnaker pipeline is executed to install the chart in Kubernetes, leveraging Spinnaker's native Helm support. The first Spinnaker pipeline stage reads the chart from S3 and renders it as YAML, passing any environmental specific configuration override specified in the pipeline. The last Spinnaker pipeline stage applies the rendered Helm YAML to Kubernetes and waits for all of the new resources to stabilize. So from commit to deploy, developers never need to interact directly with the low-level Istio or Kubernetes primitives, all thanks to the complexity abstracting power of Helm. So let's end this talk by reviewing what we learned. We looked at the good parts of Helm, particularly its templating powers. We saw how Helm can abstract Istio complexity behind a domain-specific language. We used that domain-specific language to simplify the book info demo, including mutual TLS and egress policies. We then learned how Helm Starters can help accelerate Helm adoption by introducing the Helm Starter Istio. And finally, you saw how Helm fits into a larger GitOps workflow for managing Istio services with Spinnaker. Thank you very much for this, coming to this talk.